It's like a really good project system. I was yeah. We did it down this but it's free. Okay, you have to say this. That's a lot of I thought that's like one time I lost it. Yeah. But the cruise that she gave us, like, it's really good. It's the I didn't think it hurt at all. You should stay. That's like better than you just were happy. But still, yeah, I just want and I can't say, yeah, so, you know, yeah, exactly, that's how you do it. I was hoping I could be for and they changed Boston, but right now it's really bad. And so one of the receptionists, like he was like, oh yeah, I'm just like the car really quickly. He drove off.
So in case you have any questions, feel free to actually post it on the slide, okay?
Yeah, you know, I like one mistake. That's my they just they were short their thing.
Okay, so let's get started. Okay, so on the board, I actually post a few things that I think you want to actually pay attention to it. Okay, first thing is actually the midterm 2. I know many of the students actually taking the exam today and tomorrow. Okay, but it will be open on Thursday morning AM, and you have time to review your midterm 2 all the way to next Tuesday. Okay, so it will close on next Tuesday at 8 AM. Okay, so tomorrow I will actually make a post. So remember, for the midterm 1, we have this revision period, right? That you actually show me that, okay, how you get your answers, and then to prove it, actually you know how to actually solve the answer by you just make some calculations errors. Okay, so in that case, you're going to get some partial credit back. Okay, so we're going to do the same. And in our first experience, okay, I feel like some students actually get confused about the date. So I'm going to make it very clear. So I'm going to make a post on Teams to specify, okay, when you'll be allowed to actually submit your corrections for partial credits. Okay, so that's actually the first thing. Second thing is that that's actually first and second thing, okay. Third thing is actually there will be no in-person lecture next week. Okay, so I need to actually take care of my family members, okay. And so I will actually post the in-person lecture recordings on Teams. So make sure you actually watch those recordings schedule, okay? We are actually almost done with this semester, right? So that's only 9 chapters for CHEM1312. Okay, so after we finish the midterm 2, we finish actually 6 already. Okay, there's actually 3 more chapters to go. Okay, so chapter 16 is the things we're going to go through this week. Okay, chapter 16 is actually probably actually the easiest chapters of the whole semester. Okay, calculation wise, it's actually very straightforward. Okay, and we probably will spend 2 lectures, including today. Okay, 2 lectures to finish that. Okay, and after that will be the chapter 17, which is talking about the electrochemistry. Chapter 17 is actually the most calculation heavy chapters for your midterm 3. Okay, again, we're going to spend 2.5 lectures talking about that. Okay, which 2 of it will be actually recorded online. Okay, and it is not difficult. The most difficult one is actually the midterm 2, right? This morning I actually checked with the camp manager, and then have a peek about the grade that we have so far for the midterm 2. Okay, so far our sections has the highest average grade for midterm 2. Okay, but I don't know how it will progress. Okay, we only finished 1.5 days. Okay, but we're actually leading the midterm 2 for now. Okay, and the very last chapter for midterm 3 is actually chapter 18. Okay, chapter 18 is actually a lot of memorizations. Okay, but I actually provide some my personal tips, which is you're not going to get those tips from the textbook. Okay, it's all purely from my personal experience. I feel like there's certain ways you can actually make the prediction robustly and correctly for your homework and exams. Okay, so if you look at these schedules, right, it will take us around 6 lectures to finish all the things that you need to learn for your midterm 3 and the final. Okay, and there are still 8 lectures until your midterm 3. Okay, so we're going to finish everything in 6 weeks. in 6 lectures. Okay, let me make sure we have 2 extra lecture times, right? So those 2 extra lecture times are time I want to prepare you for your midterm 3 and final. Okay, so if we include in the lecture time in the very last week before your final, okay, we actually have 10 lectures. Okay, but we want to cover everything within the first 6 lectures. Okay, and we're going to use the remaining 4 to go through the content that you should know from the very beginning of the semester. Okay, so those 4 lectures I think will be actually very useful for you when you want to actually prepare your final. All right, so make sure you participate. Okay, and I also expect that we are going to have some extra time, okay, because I don't think it takes us 4 in-person lectures to cover everything that you need to know for this semester. Okay, then we're going to talk a lot more about what are the important things for your future. Okay, so specifically, I want to talk about when you should actually export recommendation letters. Okay, so after you graduate, okay, there is something that you need to do. You always need to get the letters from someone that you trust and someone who know you to write the letter for you. Okay, so we're going to talk about, okay, when is actually a good time to reaching out? What are the things that you need to provide to export a letter? Okay, so that's actually one thing that I will actually share with you. Another thing I want to share with you is that I've been writing recommendation letters for students for many years. Okay, and then I actually receive a lot of those evaluations from all different kinds of schools. Okay, so I want to share with you that what are the schools looking for. Okay, I'm going to actually give you a list. Okay, it's actually the things I received from one of the university, and those are the things they cares about. Okay, I want to share those information with you so that you know how you can actually work on your own, based on your own schedule. Okay, toward those important personalities that the school is actually looking for. All right, so this is actually a quick summary about what's going to happen in the remaining of the semester. Okay, there's only 10 lectures remain. Okay, so any other questions before I actually start today's lecture? No? Everybody's fine? Oh, sure.
So, in Chem 1, I remember there was like this, I would say weird time period where we had 3 chapters on our 3rd midterm, but then we had extra information that we learned that would only be on the final. Will we have a case like that, or is it just gonna be 16, 17, 18?
So if you look at the syllabus, okay, so for the midterm 3, you actually do not finish the whole chapter 18. You actually finish half of the chapter 18. Okay, and then you have another week to finish another half of the chapter 18, but I feel like it's not necessary. Okay, we actually finish actually way earlier than that. Okay, so, but anyway, all the things you need to know is read from chapter 10, 11, 12 for midterm 1, right? 13 to 15 for midterm 2, right? 16 to 18 for midterm 3, and then collectively become your final. Okay, so those are the things that you should know. Okay, so any other questions? So if not, let's talk about chapter 16 then. Okay. Chapter 16 is actually a very interesting chapter because it's like something that I guess most of you haven't actually had experience before. Okay, so far the things that we have learned, which including the concentration, including the equilibrium constant, right? Including the small x approximation. Those are the things that you probably heard of to a certain degree when you were young. Okay, what we're going to talk about today is actually it's going to prepare you for the more advanced subjects when you actually enter your senior year. Okay, so it's more related to something called the thermodynamics. Okay, so this chapter starts with a very unique concept called the entropy. Okay, so how many of you actually heard of entropy before? Okay, so what is entropy? I ask the same question every year.
Is it like the basket? Different ways it can like go to a lower energy. I don't know.
Yeah, so let is actually a very good initial statement already. Okay, because when you are young and including in other sections, okay, so most of the professors when they teach Gen Chem, they always say, okay, entropy just a representation of randomness, right? And then they're going to give you some examples about like why things actually like to become random, or they will just say things like to become random, just like in your home, right? So, but there's actually a deeper understanding of these things, like entropy. Okay, so in nature, things always like to go down to the lowest energy state. Okay, so excited state is never known, right? You can become excited, but only for a short amount of time. Most of the time, you actually stay low, right? So that is actually the things that scientists or humans have observed so long. Okay, so we realize that you want to always go to the lowest possible energies. Okay, and later we're going to learn that specific energy have a name, right? Which is the free energy. Okay, so free energy is actually consider is actually the total energy sum of all different kind of energy that you can have. Okay, so the nature like to minimize the free energy. They want to move in a direction that can actually make the free energy as low as possible. Okay, and then in the free energies, it mainly contain two terms. One is so-called the enthalpy, okay, which is actually things that you have learned in your Gen Chem 1 delta H. Okay, so basically what it calculates actually the bond energies between the atoms, if you actually specifically focus on the chemistry reactions. Okay, so the other term that contribute mainly to your free energy is the term called the entropy. Okay, so again, it is actually an energy term. Okay, but this term is actually specific. Is actually especially sensitive to the temperature. Okay, so entropy is actually something always go with the temperature. Okay, and like you say, the physical meaning of entropy is actually the way the nature can actually dissipate the energy. Okay, the more way you can actually dissipate your energies, then it will happen more frequently. Okay, so how many of you actually heard of this term called the quantum chemistry? And you must have a quantum chemistry, right? But what does it mean? Okay, quantum chemistry is actually a very interesting subject. Okay, it's purely created by human beings. Okay, so we have some idea about what is actually the underlying world should look like. Okay, even though we cannot see it, but we think it must exist. Okay, and then based on some simple principles, okay, you start to build up this molecular orbitals, atoms, molecules. Okay, so you build up things actually bottom up. Okay, then you can start to predict what you're going to observe. Okay, so that's actually the beauty of quantum chemistry. And then he actually described many of the things that even though we cannot see, but once it become big enough, then you can actually use that simple principle to describe why that's actually the things we're going to observe. Okay. One very important concept from there is that if you have more way to let one thing to happen, then that process will most likely become spontaneous. Okay, so how many of you actually play this game called the I know you guys played this before, okay? Like the marble game, okay? You have a machine, right? You kick your marble all the way to the top and you start to fall, right? And at the bottom you have all this little slot, right? So let's say you have 20 slots. Okay, think about this. If you predict whether things going to happen, okay? Then if you have more slots that indicates it's going to happen, okay, then the chance it's going to happen will become bigger. Okay, so the entropy is more like that. Okay, so if you have more slots, it's designed for something to happen. Okay, if you have more pathway to get to there, then you have higher chance to make it happen. Therefore, it becomes more possible. Okay, so entropy is actually a measure of life. Okay, so if you have a higher entropy, means actually, okay, the molecule can go through less specific destination through many different pathways. Okay, so that is actually a big concept that we need to learn. Okay, so entropy is the first most important thing that we learn here. Okay, and the first thing that your textbook describes is that, okay, so considering different phases, okay, how the entropy will change accordingly. Okay, so we compare the solid, liquid to gas. Okay, so for the solid, the biggest difference between your solid and the gas is what? The gas actually move freely, right? The solid stay at one single locations, right? Yeah, so gas molecule can actually do all different kind of movements, right? So yes, allow more different pathways. It can actually evolve to store the energy. Okay, so that's why the first rule I want to learn here is actually, if I give you certain molecules, okay, in different phases, you should be able to predict which one has the largest entropy. Okay, and the gas molecule always have the largest entropy compared to all other phases. Okay, so gas has larger entropy, way larger entropy than the liquid. Liquid is going to have larger entropy than your solid. Okay, so that's actually the first things that we need to learn from today's lecture. Okay, and then if today your molecules is actually under the same phases, okay, for example, they all exist in the liquid form or both exist in the gas form. Okay, so who is going to have a larger entropy? Okay, and the answer is that the more complicated molecules have larger entropy. Okay, and we're going to see some example like this very soon in the first example. Okay, and then can't skip B. Okay, so B is actually if you compare a reaction. Okay, so one side has liquid, one side have gas. Okay, for example, your reactant exists in the liquid form, your product exists in the gas form. Okay, then you maybe ask that, okay, which is your reactant or product has larger entropy? Okay, so which side, whoever side actually have a larger total number of gas molecule will be the side that's larger entropy. Okay, so those are the three simple rules that we need to actually use to solve some of the questions here. Okay, let's look at this. Which one has the largest entropy? Okay, so the first example is actually 1 mole of HCl gas versus 1 mole of HBr gas. Okay, so our rule number 1 tells us if you have different phases, then the gas will be the one with the largest entropy, right? But here both are in the gas form, right? And the way you know is actually they're actually all in the gas form. Okay. So now it's actually since they're in the same phases, then you compare which one is more complicated. Okay, when we say more complicated, you can also translate into whoever has a larger molecular weight will be the more complicated one. Okay, so if you compare this, right, you can know that the BI is actually lower in your periodic table. Therefore, the HBr will be the one that's more complicated. Therefore, HBr will be the one with larger entropy. Okay. So that's actually the first example. Second example, you have a reactant CH3OH in the liquid form. Okay, interact with the oxygen in the gas form. That's going to give you a CO2 gas and then 2H2O gas. Okay, so which side has a larger entropy? Okay, So if you encounter a question like this, the things that you need to do is actually to count the total number of gas molecules on both sides. Okay, so if you look at this, the total gas is actually 2/3 on the left, right? So you actually judge by the coefficient. Okay, on the right, you have 1 mole of CO2 and then 2 mole of H2O, both in the gas form. So therefore, you know, you're going to have 3 moles of gas molecule on the right. Okay, so since the product side has larger total gas molecules, therefore your product side has larger entropy. Okay. So the third, any question for this? No, okay. So the third one. Okay, 1 mole of NO2 gas versus 1 mole of N2O4 gas. Okay, so you can see that N2O4 has more atoms, right, compared to the MO2. Second, it has larger molecular weight. Okay, therefore, you know, N2O4 is actually the more complicated molecule. Therefore, it's going to have a larger entropy. Okay, so it's actually very simple predictions, right? So, but this actually make all this chemical equation have another layer of meanings now. Okay, so previous we never actually care about the entropy by simply looking at the equation. Okay, but now starting from this week, when you read your chemical equations, okay, you can start to think, okay, by simply looking at the equation and then the associated basis, you can start to see, okay, product size actually have larger entropy or smaller entropy. Okay, so this is actually the first concept that we should have today. Okay, so it should be very simple, right? Okay, any questions? Okay, but now let's go to the second thing. So I just mentioned that the ultimate energy terms that we're going to use is called the free energy. Okay, and then one very important thing about free energy is actually it can actually predict the reaction is going to move to certain directions. Okay, so you must have this. You must heard these things before, right? Spontaneous processes. Okay, so what does that mean? What does spontaneous process mean? Instantly? No, it's not instantly happen. Okay. So outside forces. Okay, so it's going to happen naturally. Okay, so nature is actually have many interesting design. Okay, and thermodynamics is actually a subject that summarize those principles. Okay, but we don't know why. Okay, it is not something that we create, it's actually something we observe. And then we summarize our observation and give out some simple rules. Okay, people have observed this thing for hundreds of years. And people always try to find out some exceptions, but we have failed in the past 200 years also. Okay. So one very important thing is that nature tells us, okay, when things happen, some things is going to happen unidirectional. For example, when you have apple, if you release apple right here, it's going to fall down, right? It's not going to the other direction. Okay. When you put a hot object with a cold one, okay, eventually the temperature will fall in between the two. Okay, so this is going to happen within some simple patterns, and it's actually unidirectional. Okay, so to predict, okay, just to predict, okay, whether the things will happen spontaneously, okay, there's actually some parameter you can use. Okay, and the parameter that scientists find out is actually called the delta G, or the free energy. Okay, if your delta G is negative, then we know this process will happen spontaneous, meaning you don't need to actually do anything. It will just happen. Okay. So how do you actually get these things called the delta G? You actually start from the concept of entropy. Okay, because we know the nature like to maximize the entropy. right? So that we can really make the things always happen to a specific direction. Okay, so we call these things called the delta S universe. Okay, so now we actually introduce something that's interesting. Okay, but I don't know how familiar you are with these things. Okay, so when you do experiments, okay, what other experiment you guys are doing now? KSP. Okay, so you mix solution together, right? And then you see precipitation. Okay, so those are the things you are doing, right? So the things you're actually mixing together and the things you're actually looking at, we call it as system. Okay, so let's actually system can be actually you can define whatever system you like. Okay, but system is actually the things that you're actually watching it. Okay, you're doing all these observations. We call those things a system. Okay, but the nature doesn't only care about your system. The nature was actually composed by the system and the surrounding. The surrounding is actually everything that you don't look at. That is actually surrounding. Okay, so your system together with your surrounding, they become the universe. Okay, so you can consider every single thing is a universe. Okay, so if the universe tells you the overall entropy of this process is positive, then it's going to happen. Okay, so that is the concept that thermodynamics want to teach us. Okay, does that make sense to you? Okay, so let me emphasize this again. Okay, the things that you're looking at, okay, we define as a system. The things that you are not looking at was defined as surrounding. Okay, but in order to actually make sure that things is going to happen as the way that you predict to happen, you need to actually look at the overall, which is actually the system and your surrounding all together. Okay, so once you combine these two, we call them as a universe. Okay, so if the entropy of the universe, okay, is positive, okay, then we know there's actually a good chance that the things that you're interested in is going to happen. Okay, so that is actually the fundamental physical meanings of this delta S universe. Okay, so I summarize this relationship right here. The delta S universe, yes, free energy. Gives free energy specifically. Okay, so let me write these things down. Okay. All right, so your delta S universe is simply the sum of delta S system and then delta S surrounding. Okay, so let's actually count the things that you need to actually memorize. It's actually quite straightforward to understand what system means, what surrounding means. Okay, then you can actually easily write out like delta S universe. Okay. The what? Okay, so that's actually the entropy, right? That's actually the things that you learn in Chem 1, okay? So right now we're talking about the other thing called the entropy. That's actually your delta S. Okay, so these are the two different terms. Okay, and one is actually, this time you'll know the definition of delta S. Okay, we're going to talk about it right now. Okay. Okay, so here, I guess, right now we start to see delta S universe is actually the sum of delta S system and delta S surrounding. Okay, so system and surrounding, they actually talk to each other. Okay, and the way they talk to each other is actually using a mean called the heat. Okay, so sometimes you see the symbol of Q, or under constant pressure, people will actually use delta H. Okay, to represent the heat transfer between your system and the surrounding. Okay. So one thing that you want to be careful is that There's actually a negative sign here. Okay, so the reason you have negative sign is that when we talk about the delta H, it's actually delta H of the system, right? When you actually transfer to your surrounding, okay, you need to actually change the scope. Okay, so one is actually giving out the delta H. Okay, so your system is giving out the delta H. But from your surrounding perspective, it's actually surrounding is going to receive the delta H. Okay, so once this happens, what you need to do is actually change the sign. Okay, the negative delta H means actually coming from your system that go to your surrounding. Okay, so there's actually sign changes in this equation. Okay, so then this d delta H. Okay, now you can use actually delta H is actually parameters from your system. Okay, so once you do that, then your delta surrounding now can be actually revised using a term that's actually from your system. Okay, so once you do that, you can actually multiply the negative t on both sides. Then you got this. Okay, so what I do is actually I multiply negative t on both sides. Okay, so that's why you have the negative t delta S universe is going to equal to negative t delta system now become plus delta H. Okay, so this is actually where you got this equation. And then we define this negative t times your delta S universe as delta G. Okay, so that's actually a definition of your delta G. That's a definition of your Gibbs free energy. Okay, so delta H again is actually a term that you are very familiar with. Okay, and then here you have your delta S system. Okay. Okay, so once you have this, okay, if you replace this one with your delta G, then you got actually this second equation. Okay, so this is actually delta H. So this will be just minus T delta S. Okay, so let's actually how you get this delta G equals delta H minus T delta S. Okay, so this is actually one of the most important equation for this chapter. Okay, so delta G equals to delta H minus T delta S is equations that you must memorize for this specific chapter. Okay, so let's actually the first one equation that you need to actually memorize. Okay. Okay, so the things we are going to encounter to testing all these concepts, okay, we're going to go through those examples today. Okay, it's really to calculate your delta H, delta G, delta S, okay, for a chemical reaction. Those are something that you're going to see very often for this chapter. Okay. Any questions so far? Does everybody understand the things I talk about? Because it's actually not something that you see every day. Okay, so it's really that is actually a core of the thermodynamics. Okay, and students always get confused when we start to talk about the system surrounding. Okay, so this is actually more abstract concept. Okay, it sounds abstract, but once you actually understand it, it actually becomes very useful. Okay, and it will actually help you understand the chemistry world greatly. Okay, but with that being said, let's look at this. For a combustion of acetylene at 298.15 K, okay, so this is actually the equation is talking about. Calculated delta S universe given delta S system equals to a value, delta H system is another value. Okay, so what are the keywords here? So delta S not universe. Okay, so when we see this delta S not universe, the first thing we're going to write properly is this, right? So the things that we have learned is that universe should actually equals to delta S naught of your system plus delta S naught of your surrounding, right? So that's actually something that you should actually know. Okay, so delta S universe is equal to delta S system plus delta S surrounding. Okay, but previously we also say distance. Okay, delta S surrounding can be rewritten using some other parameter, right? So the things we say is that delta S naught system, the second term can be written as delta H over T. Okay, so this will be delta H naught. Okay, so the delta H naught is actually the heat transfer from your system to the surrounding, right? And then you divide it by the temperature. That is actually a definition of your delta S surrounding, right? Everybody follow this? Okay, so this actually kind of definition of delta S surrounding is actually the heat transfer, okay, negative delta H naught over the temperature. Okay, so that is actually the mathematical expression for your delta S surrounding. Okay, so that by doing this, then you can write this delta S naught universe is going to equal to delta S system minus delta H over the temperature. Okay, so once you have this, then you check what other information was available. Okay, you can see that delta S naught and delta H was actually provided inside the questions, right? It also provide you the temperature. So all you need to do is actually just plug in those numbers. Okay, so delta S naught system is 194.6. Delta H is negative 2511.2. Temperature is actually 298.1. Okay. So once you do that calculation, you should be able to get one thing that you want to be careful here is that pay attention to the unit. Okay. When people giving the value for your delta H, typically it's in kilojoule. Okay, but when they give you the numbers for the delta S, typically it's in joule. Okay, that means this is a unit of joule per K. Okay, here is actually kilojoule. So you want to actually multiply 1,000 so that they have the same unit. Okay, so this is actually the part that many students actually make mistakes. So make sure you don't do that. Okay, multiply 1,000. Okay, so once you do that, and then you do the calculation, it will be negative 194.6. The second thing is plus 8422.6. Therefore, you get the answer of 8228 joules per K. Okay. So this is actually really testing whether you have the concept that your delta S universe is the sum of delta S of the system and surrounding. It also tests you that do you understand the definition of your delta S surrounding is negative delta H over T. Okay, so if you do have that, then it becomes a very straightforward question to answer. Okay. Any questions for this? Okay, so if not, question number 3. So this type of question typically give you a table, very long table. Okay, it's going to give you one chemical equation, and then ask you to calculate the delta S, delta G, and delta H of the specific reaction. Okay, so when you calculate the things, Then I want to emphasize that delta S, delta G, delta H, they are extensive properties. Okay, meaning that if you double the coefficient of your substance, your delta S, delta H, and delta G will be doubled. Okay, so coefficients matters a lot in these calculations. Okay, so make sure you know you don't forget about your coefficient. Okay, and then the way you calculate your, I use delta X to represent all these three quantity. Okay, it can always be calculated by, okay, into summing up okay, so it's always computing the difference between the product and your reactant. Okay, so the X can either be S, G, or H. Okay, and the C is actually a coefficient in front of the species. Okay, so you need to add up all the species from your product side minus all the species from the reactant side. Okay, then you can just get the correct numbers. Okay, so let's use some examples so you can see these things better. Okay, so here, this is actually a chemical equation that you have. Okay, and then this is actually a table you want to do, right? So if you look at delta S naught, okay, then you focus on the specific column, delta S. Okay, and then you look at the species that you have is actually H2 in the gas form. Okay, so it will be this quantity. Okay, O2 in the gas form, then there will be actually it's delta S naught. Okay, and then H2O in the liquid form, then you know those are the numbers that you want to use. Okay, so to calculate the delta S naught for the reaction, it will be the sum of your product, right? So what is your product? In this case, the H2O in the liquid form, right? Yeah, so you know the coefficient is 2. Delta S naught of your water is 69.91. Okay, so that's all you need to put for the first term. Okay, then you're going to subtract, okay, the second term, you're going to have your H2 and O2, right? So the H2, you have the delta S of 130.5, right? So you know 2 times 130.58. Okay, and then oxygen, you have one more. So 1 times 205.0, right? So this is actually how you write down those values together with its coefficient. Okay, so once you do these calculations, then you know your delta S naught will give you a value of negative 326.3 joules per K. Okay, so this is actually how you do this calculation. Similarly, you can do the second one, delta G naught of the reaction, right? So again, delta G naught, then you need to use this column, okay? That means actually you need to use this, this, and this to do your calculation, okay? So coefficient of your product is 2, okay, for H2O. Coefficient, okay, so the value of your delta G naught formation of H2O is negative 237.13. Okay, so let's actually the first term that you need to write. Second term, 2H2, okay, 2 times H2, the delta G naught formation of your H2 is 0, okay, plus 1 times the delta G naught formation of your O2 gas is also 0, okay, so you know, by doing that, you can calculate your delta G naught is going to equals to negative 474.26. Okay, so here should be the kilojoules, okay? So this will be kilojoules. This is joules per K. All right, so very similarly, the same thing for your delta H naught. Okay, for the reaction is actually 2 times into the delta H naught formation of your product is negative 285.83 minus 2 times 0 plus 1 times 0. Okay, when you do the calculation, you got a value of negative 571.66 kilojoules per mole. There will be your delta H naught. Okay. So the key here is actually really let you know, we want to calculate the delta S naught, delta H naught, the G naught of a reaction. You always compute from the sum of your product minus sum of your reactant. Okay, don't forget about those coefficients. Okay, that's all you need to do. Okay, so calculation-wise, it's actually very straightforward and simple. And all these things are extensive properties, meaning if you change the coefficients, all this value will change accordingly. Okay. Any questions for this? No? Cool. Okay, number 4. A particular reactions have delta H naught of a certain value, delta S naught for another value at certain temperature. Assuming that the delta H naught and delta S naught hardly change with temperature, determine the temperature in degree C, which the spontaneity of this reaction changes. Okay, so this is actually a question you're going to see in your homework, in your quiz. Okay. And this is actually things that most of you don't have a good idea what it means. Okay. Spontaneity of the reaction changes. Okay, so how do you actually interpret this? Okay, so previously we say the nature will actually make the reaction to occur spontaneously if your delta G is negative, or if your delta S universe is positive, right? So that the things will happen spontaneously. So what is the condition that the reaction will not happen spontaneously? Okay, the one, so you say things actually happen in this direction. It is spontaneous, right? And then under this case, is actually if you compute the delta G or delta H, then your delta G will be negative, your delta S universe will be positive. Okay. But it also means that if you go from here to there, your delta G will be positive, your delta S will be negative, right? It is actually two sides. Okay, so we say it's actually moving to unidirectional. And then when we move to the directions, your delta S universe will be positive, your delta G will be negative, right? But it says in another way is actually the reverse direction is actually the opposite, right? So let's focus on delta G. Okay, so if your delta G is negative, it's going to move to that way. Okay, if your delta G is positive, that means actually it's going to move to this way, right? So the spontaneity will actually change right at your delta G equals to 0. So that is actually the most important information one of those few words. Okay, so when it says the spontaneity of the reaction changes, okay, you need to actually learn what you're trying to say is actually your delta G is going to be equals to 0. Okay, a very, very important concept that you should have. Otherwise, you don't know how to actually handle this. Okay. So that is actually the first most important things that you should know. Okay. So the next is actually become very simple because the next is actually the first equation actually to memorize for this chapter. Okay. Delta G is going to equals to delta H minus T delta S. Okay, so you're going to use this relationship to actually figure out the temperature. Okay. So if you read your question again, right, it gives you this. Your delta H naught is -10 kilojoules. Okay. Your delta S naught is -500 joules per mole. Okay, and all this value was determined at 298 K. Okay. And then he tells you the delta H naught and delta S naught doesn't really change with temperature. Okay, meaning if you change the temperatures, your delta H naught, delta S naught stay as a constant. Okay. Then he asks you under what temperature, okay, what temperature where you're going to see the spontaneity of the reaction changes. Okay, so what it means actually this need to equals to 0. Okay, so let's actually what it means in terms of describing the equation. Okay, so what you do is actually really put your delta G equal to 0. So 0 is going to equals to your delta H, which is -10. Okay, and then minus the temperature is actually things that you want to solve. Okay, and then your delta S is -500 joules per mole. Okay. Did I think anything wrong here? Yes. So it's very important that you don't miss like kilojoules. Okay. So this, right? So you know here should be 0 equals to -10 times 10 to the third millijoule. Okay, so don't forget about like unit consistency between the two. Okay, so this is actually the only unknown, right? So you know your T will simply equals to 10 times 10 to the third divided by 500. Okay, and then you're going to get a value. Okay, maybe I should put the negative sign so you don't feel confused. So you know the temperature will equal to 20. Okay, so in all this calculation, the temperature has a unit of Kelvin, not degrees C. Okay, but the question is actually asking for the temperature in degrees C, right? Therefore, you know to convert the Kelvin to degrees C, what you do is actually minus 273, right? So this is in Kelvin. Okay, so Tc will be your temperature in Kelvin minus 273. Then give you a value of -253 degree C. All right. So this is actually how you handle these type of questions. Okay. The key here and the most confusing part here is that the change of the spontaneity of the reaction. Okay, so to translate into delta G equals to 0. Okay, so that's actually the most important thing that you need to do. All right, so that's actually how you solve question number 4. Okay, Question number 5 is a very, very similar questions. Okay, you're going to apply exactly the same concept and approach. Okay, so solve this at home by yourself. Okay, just serve as a practice purpose. Okay. The next thing we want to talk about is question number 6. Okay, any questions so far? Oh, okay, it's very simple, right? Question number 6, given the following data, okay, it gives you 3 equations, and each equation it has your associate delta G naught, okay, and you want to ask you to compute, okay, the delta G naught formation of this specific reaction, okay. So the question is like, okay, I give you 3, look like more or less random equation, okay, and I give you a target equation, okay. I want to actually compute the delta G of the target equation from the 3 that I gave you. Okay. So how do you actually do this type of questions? Okay, the first step is that you need to know what are your reactants, what are your products. Okay, so starting from your target equation and work backwards. Okay. For example, these specific equations, you should know that this is actually your reactant, that is actually your reactant, right? And then the coefficient of that reactant is simply 1. Okay, so those are the things that you should actually pay attention to. Okay, so start from here. You want to actually looking for the equation with known delta G naught. Okay, contain that reaction terms. Okay, so if you look at it, you should be able to identify the N2O only show up right here, right? So for that equation number 3, you can see you do see your N2O, and it is indeed show up on your reactant side. Okay, but it means actually you don't actually flip the chemical reaction. Okay, you can probably actually use it. Okay, so therefore you know I can write this thing down, right? 2N2O, yes, they give you 2N2 plus O2, where I know the delta G naught of this reaction is negative 202 joule. Right. And then you start to looking at, okay, does the other two have N2O? And the answer is no, right? There's actually only N2O that you're going to see, right? What it means is actually, in the end, you must actually add up these 3 equations, okay, with some combinations, right? But since this one is actually only one that have your N2O, you want to actually match this equation to your target equation, okay? And soon, immediately you will see the coefficient of your N2O is different between the two, right? So what you do is actually what? You divide that by 2, okay? So you know what you need to have is actually N2O in the gas form. That's going to give you N2 plus 1/2 of your O2. And then we know once you do that, since delta G is a extensive property, right? This will become negative 101. Okay. So that's actually the first step you do. Okay, so once you're done with this, the next thing is actually looking for the second reactant. Okay, so your second reactant is NO2. Okay, then you start to looking for your NO2. That is actually only one have the NO2, right? So when you look at this, you realize that the NO2 in your target equation is actually on the reactant side, but from your equation number 1 is actually on the product side, right? That means actually you need to actually flip this equation first. Okay, and then you compare the coefficient. Your target is actually have coefficient of 1, but the equation 1 has coefficient of 2, right? So what you need to do is actually you need to flip it and then divide it by 2. Okay, so I'm going to write this. Okay, I'm going to write NO2, that's going to become NO plus 1/2 of O2 then my delta G naught is going to equals to positive 73 divided by 2. Okay. Which give you a value of 36.5. Okay. Any question for this step? Okay. You can see the sign has changed, right? So going from negative become positive because we flip the reaction. Okay. And then going from 73 to 36.5 is because we do a division of the coefficient, right? Therefore, we got this and that. Okay. So let's actually the second step that you want to have. Okay. Then you walk on to the next item, which is actually your product, right? So your product is 3NO. So where do you have 3NO? Here is actually NO, right? Here is actually NO. Okay, so in the second equations, you have 2NO. Okay, together with this NO in this equation, then you got 3, right? Therefore, what you will need to do is actually just to use this one as it is. Therefore, you're going to write N2 plus O2 that give you 2NO, where the delta G naught is going to equal to 178. Okay. So once you actually get the things all set up, okay, what you need to do is actually you adding up. Okay, so once you're adding up, N2 will cancel out. O2 will cancel out with these two terms. Okay, so you end up with N2O plus NO2 that give you 3NO. So this equation is actually your target equation. Okay, so the delta G total will be just the sum of the 3, which equals to negative 101 plus 36.5 plus 178. Okay, so once you do the calculation, then you have your delta G of 113.5 joule. Okay, so this is actually how you figure out the free energy of a target equation. Okay, so the key here is actually really know your target equation and work backwards. Okay, starting from the reactants and do it one by one. Okay, and eventually you know what is the actual coefficient to apply and what is the actual direction of the reaction you need to use to achieve your target equation. Questions? All right, so that's pretty much all the things I want to cover this lecture. Okay, so question number 7 is exactly the same thing. Okay, apply the same principle, trying to get these things done. We'll go back home. Okay. So, any questions? If not, I'm going to use the remaining 10 minutes to talk about something. I mean, related to this. Okay, I did not actually emphasize it enough. Okay. Yes. How do I get rid of the N2 and O2? Okay, so if you add up the 3, these 2 is actually on the reactant side, right? But it also show up on the product side. Okay, when they show on both sides, you can just close them out. Yes, okay. So the other very important thing I want to say is that you see I write this delta G, okay, but I did not put that little circle on the top, right? But in many questions, you see this delta G not, right? So what's the difference between delta G and delta G not? Okay, every time when you see this little circle on the top right corner of a variable, okay, every time when you actually see that in the chemistry courses, it means the reaction was measured at the standard condition. Okay, so what is standard condition? Yes. Yes, very good. Okay, so three things need to be satisfied. Okay, first, temperature has to be 25 degrees C. Pressure has to be 1 atm. Third one is actually concentration. Concentration of each species listed inside the equation has a concentration of 1 m molarity. Okay, so those are the major difference between we're gonna see this delta G naught versus delta G. Okay, so the things you want to actually get from there is that delta G naught is actually a very, very unique condition, right? You actually specify temperature, you specify the pressure, you specify the concentration of every single species inside your solution. Okay, then under less specific conditions, then you compute the free energy of lead reactions. Then you got your delta G naught. Okay. But in most of the reaction you're going to do, okay, in your whole life, okay, most likely are actually not done in the standard condition. Okay. Therefore, you typically don't put delta G naught, delta H naught, delta S naught in your calculation. You just calculate delta H, delta G, delta S. Okay. But why all the table we have has delta G naught, delta S naught, delta H naught? So why do people want to do those things specifically at a specific condition and use that as a standard? Okay, so those are the things that is actually very interesting. At least to me, back when I was young. Okay, so when I first realized that, okay, why sometimes I put a little circle, sometimes don't, right? So later I realized that the reason people to put that little circle on the top right corner is that they want to always have a defined conditions. Okay, so that it's sort of defined. Okay, if I have these specific conditions, I calculate my delta G naught. You have certain value. Okay, but we also just learned that when your system reach equilibrium, what's your delta G? 0, right? Because we just say that if your delta G is actually negative, the reaction will move to one direction, right? If it's positive, it moves to the other direction. Okay, but when the system is actually at equilibrium, what does it mean? It doesn't move, right? When the thing's at equilibrium, it doesn't actually move. Okay, so the delta G will equal to 0. Okay, it's actually a very, very essential concept that we need to actually learn for the lectures on Thursday. Okay, delta G will always equal to 0 when a system reach equilibrium. Okay, with that being said, what it really means is actually that if you see your questions, if say the chemical reaction reach equilibrium, okay, the chemical reaction reach equilibrium, how you need to write down your paper is that delta G equals to 0. Okay, so that is actually a similar way to like in our question number 4, right? So this statement, spontaneity of the reaction changes, is also indicated delta G equals to 0. Okay, so those are the very important terminologies for this chapter that you know you are going to use the relationship that delta G equals to 0. Okay, so you know once the system reach equilibrium, okay, the delta G will always equal to 0, right? Then when you actually compute the delta G naught, which is actually at the standard condition, okay, 99% of the time it's not 0. Okay, that means actually its energy is actually somewhere beyond, away from your equilibrium. Okay, so the delta G naught is actually telling you how far away your reaction is from the equilibrium position. Okay, so later on you will see we are going to use delta G naught to calculate the equilibrium constant accordingly. Okay, so those are the things that I want to actually bring it up so that in the next lectures you can understand why we have an equation called delta G naught equal to negative RT times natural log K, where K is actually equilibrium constant. Okay, so I think that's all that I want to say for today's lectures. And then, thank you. Mm-hmm.
I have a question. There's a grade on Canvas that says makeup exam and I have a 0. Do